I'm a mathematician, actually. I'm the only mathematician in this group, so I'm the boring one. And that's why they scheduled me right after lunch, so you can have a nice nap, and it's good for you. Math is good for your digestion. So, but I want to talk about mathematics and how it connects to the physical reality, and what is mathematics really about. So, I want to start with this great quote from Galileo. The laws of nature are written in the language of mathematics. And without mathematics, he says, we are left wandering about in a dark labyrinth. So mathematics has been, for centuries, instrumental in the progress we have achieved in science and technology. And in fact, some people have said even that the effectiveness of mathematics in natural sciences is almost unreasonable. Eugene Wigner, Nobel Prize winner, has said that. So that brings up a very interesting question as to what is math? Is it something that we find in nature? Is it something that we create? Why is it so effective in the physical reality? In other words, does math exist by itself without physics? And that's a very interesting question because, of course, there's so many concepts, so many mathematical concepts we come across in our experience in the world around us. I mean, we count 1, 2, 3, 4, 5. That's how we get acquainted with the concept of numbers, which, of course, is very important. We see various geometric shapes around us. But actually, for someone who's a practitioner who does mathematics for a living, you start seeing things, you start seeing parts of mathematics which do not manifest themselves immediately in any obvious way in the world around us. So I would say that, in fact, it's really kind of, he hit the nail, the Wigner, when he said that, because these important discoveries in physics have been preceded by works in mathematics, but those works were done oftentimes without any reference to physics. They were done within the narrative of the subject itself. Robert Dijkgraaf talked about Einstein's relativity theory being preceded and anticipated almost by a work of a mathematician, Bernard Riemann, 60 years earlier. So Riemann talked about geometric shapes and the intrinsic structures of geometric shapes, like a sphere or a surface of a donut, without referring to a landscape, an ambient space into which they're embedded. And people were saying, why are you doing this? Don't you know that every geometric shape we encounter in the physical world around us, every curved shape, is actually embedded in a flat three-dimensional Euclidean space? Because that's how we humans have thought about the world around us for millennia. It is flat and Euclidean. You can draw three, axes, perpendicular axes, to create this Cartesian coordinate system. And then Einstein showed that that's not the case, as we have heard already several times in these proceedings. So, in other words, that theory, to even talk about a space which is not flat, which is curved, we need a mathematical theory, because we cannot even imagine how can it exist by itself. But where is it embedded? Well, it's not embedded anywhere. It can exist by itself. But for that, you need this mathematical theory. So that's what I mean when I say that that discoveries in physics were preceded by works in mathematics. And so this is a very interesting. So this is a very, very interesting element. So then, of course, my main point then is that mathematics is almost kind of like this hidden parallel universe of elegance and beauty, which is intricately intertwined with our world. And today I want to talk about some aspects of this world of mathematics and the subtle connections between this world and the physical world, the physical reality, which we all see and love and observe. And what I really want to talk about today is this idea of unification in mathematics. In the previous lectures today, you have heard about the idea of unification in physics, where roughly you would want to have a T-shirt which would have all the equations describing all of physics written on maybe on the front and the back. Maybe it would not be enough to just on one side, but maybe on both sides. So this idea has driven so many scientists, so many physicists for many years. But actually, in mathematics, it's very similar. In mathematics, we also have this yearning almost, this desire to understand things from very few basic fundamental principles. And to find connections, find invisible connections between different parts of mathematics, which at first glance seem to be light years away. So I really want to think of mathematics as this giant jigsaw puzzle. Except you don't know, they gave you the pieces, but they didn't give you the box. So you don't know what the final image is going to look like. And you're trying to assemble that image from those pieces that you're given. And so different parts of mathematics then would be different parts of the puzzle. When you try to solve a jigsaw puzzle, maybe if you do it with your friends, maybe it's a big one, so you work on one part with some of them, then others working on some other part, But eventually, you would like to connect these parts. And another analogy is like continents. It's like different continents that we have. So let's say one subject would be like North America, and another one would be like Europe, and you're trying to find links and connections between them. So what are these different continents of math? What am I talking about more specifically? So there's number theory. The fans of Matrix will recognize this image. There's number theory. We talk more about numbers. What kind of numbers are there? And what are they good for? That's one subject, which has a long, long history, right? Then you got harmonic analysis. Harmonic analysis is best understood, I think, is in terms of as when you study sound, when you appreciate the sound of a symphony. We all realize that, the sound of a symphony, this beautiful, sophisticated sound, is actually made from different notes on different instruments. So it is, as a mathematician would say, is a superposition, or it's a kind of a composition of different pieces, of different sounds of different instruments. And each of those sounds is represented by a wave, or what we call a harmonic, a simple harmonic. And the frequencies of those waves are multiples of each other. And the idea is that when you superimpose them, when you hear different instruments, that creates this beautiful symphony. Okay, so that's the idea of harmonic analysis. And again, we'll talk more about this in a few minutes. Or another subject, geometry. So this is an example, behind me is an example of what we call in mathematics Riemann surfaces. It's the same Riemann, the same mathematician Bernhard Riemann, German mathematician Bernhard Riemann, who came up with the ideas of Riemannian geometry, so fundamental to Einstein's general relativity theory. He also developed the theory of two-dimensional shapes, like this one. Or think of a surface of a sphere, surface of a basketball, say. We'll return to that later. Those are the what we call Riemann surfaces. So you see here, I give you examples of three different areas of mathematics, three different continents, if you will, of that giant jigsaw puzzle: number theory, harmonic analysis, and geometry. They all look very different. They are driven by different kinds of problems. They are developed by different people to different ends. Could it be that they are somehow secretly connected? That there is some story behind this, which actually brings them all together? Well, it turns out there might be. And that's what I would call a kind of a unified theory of mathematics. That theory, in fact, was initiated about 45 years ago, in the late 60s, and it is now called the Langlands program. I really like to think of it as a kind of a grand unified theory of mathematics. Not in the sense that it necessarily unifies all of mathematics, but it unifies many different parts, and hopefully, and it has been, historically, has been sort of propagating to more and more different domains, different fields, and so maybe eventually other fields will be affected as well. And, but the essential part is that it does connect these different continents of mathematics. Robert Langlands, the mathematician who initially initiated this theory, who started developing these ideas, Robert Langlands, Canadian-born mathematician who's a professor at the Institute for Advanced Study. Here he is at his office, which incidentally is the office formerly held by Albert Einstein. So I always kind of, as a half joke, I always say, everybody knows about Einstein and his theory, but very few people know about Langlands and the Langlands program, which I think one could argue is just as fundamental to humanity as Einstein's general relativity theory, or his works on relativity theory and other works, which is a very nice office, by the way. So as Robert Dijkgraaf can attest, I have collaborated with Langlands, so I've been there. Just a little name dropping.